Alright, so today's lesson we're now going to take the mean value theorem, which we have learned for derivatives, and adjust it to be a mean value theorem for integrals, since there's a direct relationship between the derivative and the integral. Now let's remind ourselves of the original mean value theorem. And in the original mean value theorem, so we had the conditions that were necessary for the mean value theorem, that if we had a function f that was continuous on the closed interval and differentiable on the open interval, a to b, that what we knew is that at some point in c, for some c in the interval a to b, it had to be true that the instantaneous rate at that value c had to equal the average rate of change over the entire interval. So we would set up our formula and we would solve. So at some point, the average rate of change was equal to the instantaneous rate of change. So now what we're doing, because we're working with our integrals, what I want to do is kind of remind you of something. And this is where we want to be very careful in calculus, because there's several things that are going to start to sound alike and you may get confused. But first, let's talk about what we're looking at here. We're going to start talking about something called the average value of a function. The first point that I want to make is that the average value versus when we say average rate of change, that these two, if we're talking about the average value of a function f of x, that is not the same thing as the average rate of change of that function f of x. Okay, what we basically mean when we talk about the average value, that's kind of the idea. How do you find an average? To find an average, what you basically want to do is you want to add up all the y values. So I'll say sum y sub I for all the y values on your interval. We'll say I equals 1 to n. And obviously, if I'm adding up all the y values on a function on an interval, there are infinitely many of them. So we could think of this as we're going to have to take the limit as n goes to infinity, so that we add up infinitely many of these y values, and then we would take that value and we would divide that value by n, by the number of values that we had. And that if we were to take this, we would get the average of the y values. That's what we mean when we talk about the average value of the function. Now, hopefully you can see that they're going to give you a formula here. Now remember that the f that they're talking about here is the function in the integrand for the integral. So this actually is a quote-unquote derivative already. All right. So we're looking at the function in the integrand, and we say, okay, that function has to be continuous on the closed interval. Why do we need that requirement? That requirement has to do with the fact that, remember that if it's continuous, then f is integrable, so that we can find a definite integral using this process. And now let's remind ourselves, why is the definite integral from a to b going to equal, this is going to be your average value, which is this down here, times your b minus a. Now let's see why that is. Now most of the time when we set this up, we actually prefer to have it solved for the average value. Now let's think about this sigma notation for this. This definite integral is the limit as n goes to infinity of the sum I equals 1 to n of f of ci times delta x. And then we're taking that whole thing and we're dividing it by b minus a. Well, if you look at what we have right here, think about this delta x. Remember that delta x, our formula for finding delta x, is b minus a over n. And then remember that we were dividing this by b minus a. Now, I have it over the limit over the whole thing, but you can bring it in because it's like a constant. So I can have it outside the limit or I can put it in the limit. So I'm going to go ahead and put it in, and I'm actually going to put this divide by b minus a all the way in to inside the summation because the variable in your summation is I. So it's going to become the limit as n goes to infinity of the sum, I equals 1 to n, of my y values at each of the endpoints in our intervals times b minus a over n times 1 over b minus a. And hopefully you can see that simply by canceling this b minus a, what do we have left? We have basically the sum of the I, or sum of the y values. We're taking the limit as n goes to infinity, the sum, 1 to n, of all the y values divided by n, which is nothing more than your average value of f of x on the interval a to b. And so we added the y values and we divided by the number that we had. So this idea here of how the definite integral is related to this average value, the formula should make sense to us. Now, most of the time when we're using this, we kind of like this version of it, simply because it's a little cleaner when we write it. So when you're memorizing your mean value theorem for integrals, you're finding the average value by taking 1 over the b minus a and multiplying it times your definite integral from a to b, because that will basically add up the y values and divide by n. And so the idea that you're looking at here is that kind of this idea of, like, if you're thinking about it in an area, is if I were to find the average value, this is my average value right here, f of c, it's kind of like taking the area here in this portion and trying to find the place where if I was trying to average it out, that it would exactly fill in this area down here. So these two areas, we'll call this A and A, are equal to each other. So you're trying to find the average value of the y values giving the height there. Now, what gets confusing about this is that we have to worry about paying attention to what they're asking you for. Are they asking you for the average rate of change in the function, or are they asking you for the average value of the function? Because those are going to be two different things that we're talking about. If we do average rate of change of f of x on an interval a to b, that when they ask for that, they're asking you to calculate f of b minus f of a all over b minus a, the slope of your secant line. However, if they're asking you to find the average value of f of x on the interval a to b, then we're going to do the 1 over b minus a times the definite integral. All right, so for example, in the problem that we have down here, and this is a calculator problem, so we're going to remember that, we are looking at a temperature function, and this temperature is modeling your degrees Fahrenheit T hours after 9 a.m. So 9 a.m. is T equal to 0. And we want to first find the average temperature during a 12-hour period from T equal to 0 to T equal to 12. So you look at this, they're not asking for the average rate of change, they're looking for the average temperature. So the average value of this function t of t for the interval 0 to 12, I'm labeling what I'm finding, would be 1 over 12 minus 0, the integral from 0 to 12 of my function, 50 plus 14 sine pi t over 12 dt. And that's how I'm going to find, and I'm going to basically type this into my calculator to get my average value of the function. What is the average temperature during the 12-hour period? That's part A. We'll do it on the calculator in a second. Now we look at part B. Find the values of t for which the mean value theorem guarantees the temperature was the average temperature. Okay, so then let's think about that for a second. So what they're basically saying here is that I'm going to find this average temperature. And if we look back at our picture up here, that this average temperature, where I'm kind of shifting this area from here to here, there has to be a point in time, a C value, at which the actual height on the curve is the average value. And that should probably make sense to you, that the average value has to fall somewhere in this interval. If you are adding all your y values, some will be above, some will be below, that the y value of interest is going to fall somewhere in the middle, and that the C value, we should be able to find a time at which the function actually is the average value. And that's what we're going to be looking for here. So what we've done is we first calculate the average value of the function, which we get that, and we'll get it on the calculator. And then for part B, what we're going to do for part B is we're going to say, okay, I want to find when you actually have that average temperature. So we would take this value that we find here, and we are going to set that equal to our actual function, because I want to know when the function has that average temperature. This is the average of t, and we know that at some point in time, t of some C value has to equal this value that we're going to find on our calculator. And since this is a calculator problem, I am going to solve this on the calculator. So let's show the work on the calculator. So the first thing I'm going to do is, let me clear out some things that I had in here. Here's my function that we're looking at. Okay, so I have the 50. Let me move over so you can see it a little bit larger here. So here's my 50 plus 14 sine pi x divided by 12. So I'm going to go to my home screen and notice that what I have done is I'm going to then calculate the average value. So I'm going to do 1 divided by my 12 minus 0, 1 over b minus a. Yes, I could have done 1/12, but I'm kind of stressing something here. Then I'm going to go get my definite integral, so math 9. And we do from 0 to 12. And we go get our y1, so vars, y-vars, function, y1. And we're doing the derivative with respect, or the integral with respect to x. And so this is going to give me my average value, my average temperature over the 12-hour period. I'm going to store that in, say, alpha a, just so that I can import that value. But let's write it down to 3 decimals, so 58.913, 58.913. And units are always good when you're doing these problems, so this is degrees Fahrenheit. So we have found that the average value of the temperature over the 12-hour period is this 58.913. So now I'm going to take my function and I'm going to set it equal to this 58.913 degrees Fahrenheit, and I'm going to solve for C. And that will find the value of T that is guaranteed by the mean value theorem. Notice that this is a little different than what we did for derivatives. In derivatives, we had to find the value for which the instantaneous rate of change was equal to the average rate of change. That's a different problem than finding the average value of the function and finding the time at which the function is equal to its average value. They're two different questions. One is going to use derivatives, one is going to use integrals. And so we want to pay attention to when we're doing that. So coming back to my calculator, now that I have that stored in A, I'm going to come down and I'm going to just go ahead and import that A into my calculator. Let's pick a decent window. We definitely know we want 0 to 12. We don't know whether it goes positive or negative for your temperature values, but we're interested in where it intersects 58-ish. So we might as well go, don't really worry about the negatives so much. Let's go up to maybe 65 and go by increments of 5. And then we can take a look at our function. And you'll notice I don't have the temperature function. I do not have it on. So let's turn the temperature function on. and then take a look, you knew something was wrong because we didn't actually see the actual function we were looking at. And notice that while we're guaranteed to have at least one, we actually have two places for which we are equal to the average temperature, here and here. So we would do second calc, and then at this point we can just use number 5. We can pick a value. I'm just going to put in 1, graph, second calc. We're going to do intersect 5. Oh, first curve. Yeah, there we go. Wasn't paying attention. I was thinking I was going to do a left bound and a right bound. So first curve, second curve, make sure you're closer to one of them, and then it will find our intersection. So at 2.636 would be the first one. So this occurs at time approximately to 2.636. 2.636, or, and then we go find the other one. So second calc, intersect, first curve, second curve, and then this time my guess, I'm going to put it over here at 8. And it'll find that one, my intersection, 9.363. 9.363. 9.363. All right, so that's why it says find the value, parentheses S. It actually happens at twice. We're guaranteed at least one place where we have the average temperature, but we found 2 in this case. Now let's contrast that with if I was talking about the average rate of change. You know, this is one of those things where you have to be very, very careful and paying attention. So instead of, if I had asked instead to find the average rate of change, of t for 0 to 12, then in that case the average rate of change would have been t of 12 minus t of 0 all over 12 minus 0. And I'll leave you to verify this actually does end up being 0. If you take a look at the function that we're looking at, it's exactly if you look at your points, here's your point for 12. So if I type in 0 for trace, let's put myself on the actual temperature function. So if I type in 0, I get 50. If I type in 12, I get 50. 50 minus 50 over 12 minus 0 is 0. All right. So the average rate of change is 0. And then if I were asking you to find the value, the C value guaranteed by the mean value theorem, okay, the C value guaranteed by the mean value theorem for derivatives, that's where at some point my derivative, and I don't have an F here, so let's use the notation that we have, at some point my instantaneous rate of change on this function should be equal to my average rate of change, t of b minus t of a over b minus a. So on this one we would be trying to solve t prime of c equal to 0. So to do that problem, coming back, I would have to come in. All right, I'm going to turn off this one and turn off this. I am now going to put in my average value, which is 0. I could just do the zeros of a function. I'm going to take the derivative, the instantaneous rate. So now I'm going to do math, and I'm going to do 8. And I'm going to take the derivative with respect to x of my temperature function. So that was in y1, vars, y vars, function y1. And remember we do it when we're graphing. We're doing x. So we want to graph the entire thing. And we want to know when it's equal to 0. So I'm going to change my window because I'm basically only looking at where it crosses. So maybe let's do negative 10 to 10, just so I can look at where the x values or the intercepts are going to be on the rate function. So of course that's the 0. And then coming in, here's my rate function coming in, and at some point, it's taking a little time to graph, it'll cross here, and I could do second calc, but as you can see, where does it cross? Because it was nice and symmetric, it's crossing right here at 6. So the value guaranteed by the mean value theorem for derivatives, about the average rate of change, this value would be at t equal to 6 hours. So completely see the difference between what the two questions are asking. There's the average value of the function found by using the definite integral, and the mean value theorem says that there's a time guaranteed in the interval for which the function equals its average, versus the mean value theorem for derivatives, which finds the average rate of change by doing this, and then finds the value guaranteed by the mean value theorem by setting the instantaneous rate equal to the average rate. So one's dealing with the rates of change, one is dealing with the average value of the function. Now what can get a little confusing here, and so I just want to show this to you when you are looking at kind of putting everything together on the AP. When we get down here to, hey, every possible thing is going to be in one test, that if I have a position function, s of t, okay, so this is my position function. All right, and then I have the derivative of the position function, the velocity function. You actually, if you're being asked to find the average velocity, okay, find average velocity, you actually now are going to know two ways in order to find it. The first method of finding the average velocity is to recognize that average velocity is the average rate of change of s of t. So I could find average velocity by doing the average rate of change on s of t, which is your change in position over change in time. So you would do s of b minus s of a all over b minus a. So you can find average velocity if you are given the position function by doing change in position over change in time. And again, this is for the interval a to b. But there's now a second way to find it, that I can find average velocity for the interval a to b by taking the actual velocity function and finding the average of the velocities. So I can do that by doing 1 over b minus a, the definite integral, a to b, of v of t dt. I can find the average velocity by finding the velocity function and then taking the average. Now, why do you have two possibilities here? It depends on what you're given. I would use this method if I know s of t. If I know the position function, I am going to use the position function to find the average velocity. But if I don't know the position function, but I know the rate function, I know v of t, then I would use this. So it depends on what you're given in the problem to find it. But the average velocity is the average rate of change of the position function. Or you can do average velocity using your definite integral formula from above. So those are two ways of calculating for your mean value theorem. Okay, and I'm going to stop this video right here because that's a good synopsis or summary of the mean value theorem for integrals, and we'll pick up the next video taking a look at some examples.